Young's double-slit experiment. Interference in light waves from two sources was first demonstrated by Thomas Young in 1801. A schematic diagram of the experimental setup is shown here. Light was made to pass through a slit SO. The waves emerging from this slit was made to pass through two parallel slits S1 and S2. These two slits served as a pair of coherent light sources because waves emerging from them originate from the same wave front and therefore maintain a constant phase relationship. Thomas Young observed that the light from S1 and S2 produced on the viewing screen a visible pattern of bright and dark parallel bands called fringes. What causes bright and dark fringes? A bright fringe appears if the light emerging from S1 and S2 interfere constructively, and a dark fringe appears if the light from the two slits combine destructively at any location on the screen.
Interference of waves. The phenomena of the light which undergoes refraction and reflection can be explained by the two theories of light. They are the corpuscular and the wave theory of light. But some of the other phenomena, such as interference and diffraction, can only be explained by the wave theory of light. We know that two or more wave motions travel in space at the same time. Sometimes these two wave motions combine and some physical effects take place. Interference is one such physical effect. When two or more waves cross each other in the same medium, they both interfere and an accident takes place. This accident is known as the interference of waves. Interference is the combined effects of the disturbance caused by each individual wave at the same place at the same time. This effect can be understood from the principle of superposition of waves. Principle of superposition of waves. To understand this concept of the superposition, let's understand some of the examples. When we drop a pin in a tank, we see some circular waves. When another pin is dropped, we see some more waves. These waves travel in the same tank, and at one time or another, they superimpose on each other. The resultant wave would have an amplitude which is the sum of the displacement due to the individual waves. The principle of superposition of waves states that when two or more waves traveling through the same medium simultaneously, the resultant displacement at any point is the vector sum of the displacement due to the individual waves. In our case, the pin is dropped in a ripple tank with two pins. If y1 is the displacement caused at a point due to the first source, and y2 is the displacement caused by the second source, then the overall displacement r at the point of interference would be given by r equals y1 plus y2. When both sources have the same amplitude, then y1 and y2 would be equal to y. When y1 is due the crest or trough, and y2 is also due a crest or trough, the resultant would be the maximum. And when y1 is due to a crest and y2 is due to a trough, or vice versa, the displacement would be minimum. When maximum displacement takes place, it's called constructive superposition, and when minimum displacement takes place, it's called the destructive superposition. In constructive displacement, a maximum displacement curve is produced. Thus, when constructive displacement occurs, the phase difference between the waves would be 0, or a multiple of 2. When minimum displacement occurs, waves superimpose destructively. The phase difference of the waves would be an odd integer multiple. Interference of waves. When superposition of waves occur, they can be destructive or constructive. This physical effort, observed as a result of the superposition of waves, is called interference. The physical effect of the superposition of waves from the source vibrating with the same frequency and amplitude is called the interference of waves. The physical effect is in the form of vibrations in the amplitude of the resultant wave in a given portion of the medium. Interference is a special case of superposition of waves, which originate from different sources but have the same amplitude and same frequency.
of light waves through an aperture. In our earlier session, we have learnt about diffraction. Now let us learn how the light waves get diffracted at an aperture. According to definition, the bending of a wave or its deviation from the original direction of propagation when it meets a small obstacle is called diffraction. The wavelength of the light waves is 5000 angstrom, which is very less compared to the wavelength of the water waves and sound waves, which are about few centimeters to meters. As the wavelength of the visible light is small, comparing to the wavelength of the incident waves. Hence, for experimental observation, diffraction of light waves needs small-sized obstacles. As we learnt earlier, according to rectilinear propagation of light, when light falls on the opaque object, geometrical shadows of small opaque objects should be formed. But as the obstacles are small, the light wave bends along the corners of the obstacles and slightly spread into shadows, and thus they are not sharply defined. In the case of monochromatic light, when the light wave is incident on the small object like hair or a sharp edge object like blade, due to the geometrical shadows are formed with dark and bright fringes. Thus, diffraction is defined as the bending of light waves around an obstacle whose dimensions is comparable to the wavelength of the incident light, and hence its spreading into the geometrical shadow.
Coherent waves of light. So I have taken two waves here of an arbitrary color, and the color does not correspond to the light colors and its wavelengths. So let's take two waves of yellow and red color and let there be a phase difference between them. By a phase difference, I mean that the crest of one wave does not coincide with the crest of the other wave. So here you can see that the crest of the upper wave is coinciding with the trough of the lower wave. So there's clearly a phase difference of half a wavelength. Now, the phase difference is indicated in terms of dimensions by those two pink colored rods that I inserted there. And let us see whether the distance between these two rods is the same with time or not. So let's take a side view and play an animation to observe these waves. So let the time be on the x-axis, and the phase difference between these waves is also represented on the x-axis. You can see those pink rods again, and it's very clearly seen that the distance between those two pink rods, which denotes the phase difference, is not changing with time. The distance is remaining the same. The pink rods are not getting farther apart from each other or closer to each other. So these two waves will keep on traveling forever in this manner. The resultant wave, of course, will be a straight line. Let's look at it again. Now I have plugged in an arrow on the bottom showing time on the horizontal axis, and let's look at those waves again. The two waves with a phase difference of half a wavelength. So the trough of one is coinciding with the peak of the other, and you can see that the phase difference is constant with time. So such waves are called coherent waves. It's nothing to do with monochromatic waves. That's a different meaning, and that means waves of the same wavelength or frequency. So I hope this concept of coherent waves was clear. Thanks and have a great day.
Laws of reflection on the basis of Huygens construction. Let a plane wave front AB be incident on a reflecting surface PQ at an angle. In the absence of the medium, the wave front would have advanced to A dash B dash. But as the wave front strikes B, the point becomes the center of secondary wavelets. In time t, the wave front advances a distance A dash equals to Ct, and would have advanced a distance BB dash equals to CT, with B as center and radius equals to BD equals to CT. Draw a secondary wavelet shown as a part of a circle as shown in figure. From A dash, draw a tangent plane to this wavelet. Thus, A dash D is the new reflected wavefront which advances forward in the direction shown by the arrows. The angle of reflection is the angle I dash, which the reflected wavefront A dash D makes with the surface PQ, that is, angle B A dash D. Angle I dash. Deduction of the laws of reflection. The angle of incidence is the angle between the incident ray and the normal, but the ray is perpendicular to the wavefront and the normal perpendicular to the surface. Hence, the angle of incidence is the angle between the incident wave front AB and the surface PQ, that is, angle ABA dash equals to I. Similarly, the angle of reflection is the angle between the reflected wave front A dash D and the surface PQ, that is, angle I dash equals to angle DA dash B. Now, from the geometry of delta S with BD equals to A dash and BA dash common, we know that these are congruent delta S. Hence, angle I equals to angle I dash, or the angle of incidence equals to angle of reflection. Also, the incident ray, the reflected ray and the normal are all in the same place. Hence, the wave theory has proved the laws of reflections at a plane surface.